In the late 1990s, something extraordinary happened in the world of cosmology. Two independent teams of astronomers studying distant supernovae made a shocking discovery. The expansion of the universe isn't slowing down, as previously thought. It's speeding up. This observation defied expectations. For decades, scientists believed that gravity would eventually slow the cosmic expansion, perhaps even causing a big crunch, a reversal back into a singularity. But instead, something unseen, something mysterious, was accelerating the universe outward at an ever-increasing rate. They named it dark energy. This term sounds simple, but don't let it fool you. Dark energy is not well understood. In fact, it's arguably the most profound mystery in modern physics. It accounts for nearly 78% of the entire energy content of the universe. Yet we don't know what it is, where it comes from, or why it exists. So what could this elusive force be? The leading theory suggests that dark energy is an intrinsic property of space itself, the vacuum energy. In quantum field theory, even empty space is teeming with virtual particles that pop in and out of existence. These fluctuations may contribute a tiny but pervasive energy that exerts a repulsive force, causing space to expand. Einstein once introduced a concept called the cosmological constant, a fudge factor in his equations to maintain a static universe. He later called it his biggest blunder after Hubble's discovery of cosmic expansion. But now, that cosmological constant may be the very key to understanding dark energy. If the vacuum of space holds energy, and that energy has a repulsive effect, then as the universe expands, more space means more vacuum energy, which in turn accelerates the expansion even more. It's a feedback loop on a cosmic scale. However, there's a problem. When physicists try to calculate the energy of the vacuum using quantum mechanics, they get a value that is 120 times larger than what is observed. That's a number so massive, it's considered the most wrong prediction in the history of science. Clearly, something is missing from our understanding. Some scientists propose that dark energy isn't constant at all, but dynamic, evolving over time. This idea is called quintessence, a term borrowed from ancient philosophy. In this model, dark energy is a field that changes in strength depending on the conditions of the universe, similar to how inflation operated in the early moments after the Big Bang. Others believe that what we call dark energy may simply reflect our incomplete knowledge of gravity itself. Maybe Einstein's equations need tweaking at cosmic scales. Modified gravity theories, such as FER gravity or extra-dimensional models, attempt to explain cosmic acceleration without invoking mysterious energy. There's also the possibility that dark energy is tied to the geometry of the universe. If the cosmos has a shape we haven't fully grasped, one involving curvature or higher dimensions, then what appears as acceleration might be an illusion caused by our limited perspective. Regardless of its origin, dark energy is powerful. It's not only pushing galaxies away from each other, but it's also changing the fate of the universe. If dark energy remains constant or increases, the cosmos will continue expanding forever, growing colder, darker, and emptier in a scenario known as the Big Freeze. In even more extreme models, dark energy could grow stronger over time. In this Big Rip scenario, galaxies would eventually be torn apart, stars pulled from their orbits, planets shredded, and even atoms themselves ripped to pieces. Space would stretch so violently that nothing could hold together. But we're not there yet. For now, astronomers use Type Ia supernovae, exploding white dwarf stars, as cosmic yardsticks to measure dark energy's effects. They also analyze the cosmic microwave background, the distribution of galaxies, and gravitational lensing to refine their models. Future observatories like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope aim to map the universe with unprecedented precision. By surveying billions of galaxies, they will help determine whether dark energy is truly constant or if it's evolving over time. The answers they find could rewrite the laws of physics and reshape our understanding of reality itself. And here's the most fascinating part. Without dark energy, life as we know it might not even be possible. If the expansion of the universe had been too slow, matter would have clumped too quickly, forming massive black holes or collapsing into a dense, hot soup. Too fast, and galaxies would never have formed. Somehow, dark energy has exactly the right value, not too strong, not too weak, to allow stars, planets, and eventually life to emerge. This uncanny fine-tuning has led some to suggest a multiverse explanation where countless universes exist with different values of dark energy. We just happen to live in one where conditions are just right for observers like us to ask the question, why? Whether it's a constant, a field, a geometry, or something entirely new, dark energy is a reminder of how much we still don't know. The cosmos is still revealing its secrets, and every answer leads to deeper questions. At Wantin, Infinity Beyond, we're committed to exploring these profound mysteries, not just for knowledge, but for perspective. Dark energy is more than a force. It's a cosmic invitation to look beyond what we see and imagine what might lie beneath the surface. In the next segment, we'll shift our focus to dark energy's mysterious counterpart, dark matter, the invisible scaffolding that holds the universe together. Subscribe to Infinity Beyond, and let's continue unraveling the invisible forces that shape reality.